Hey everybody, this is Larry. This is day 8 of the June Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord and chat about this problem or other problems, whatever you like. And today's problem, we're going to go over construct binary tree from Preorder and Inorder Traversal. So my disclaimer is usually that I'm solving these live, so it's a little bit slow. I go in weird directions, just watch it on 2x or whatever you need to do. Go back if you need once in a while, whatever. You have the technology. It's the internet. Anyway, so yeah, just a daily update is that my AC isn't quite working today. It's 90 degrees Fahrenheit, which is I think 32 degrees ish in a normal degree for anyone using a reasonable system. But in any case, so it's very hot and there's no AC. And yeah, that's all I have. I need to fix it. I mean, it's fine. It's just that I've had the same AC for like 10 years, and I'm trying to figure out whether I should replace it or because there's some economic or benefit with efficiency or something like that. With I don't know how much it cools the whatever, but then I don't know. Who knows? I might move it. I don't want to buy a air conditioner right before I move. Then I would have to move that too. Anyway, all right. That aside, in case for the two people who are going to ask me about it, that's my update on that. Anyway, so today's problem is construct binary tree from Preorder and Inorder Traversal. Let's see. Given two arrays Preorder and Inorder, construct and return the binary tree. Okay. So yeah, so definitely. Okay, so unique is the keyword here, but yeah, definitely this is a problem that is, I would say, well known. I mean, I'm not to say it is easy. It is just well known. So, yeah. Given that n is 3000, in certain language n squared is going to be too slow, and in either case you should strive to be not n squared, which is 3000 squared. Probably, to be honest, if you use a fast language, it's fast enough. But then in Leetcode, it uses the sum of the execution time versus just execution time. So you might run into some issues there as well. But so whatever. But that's just the judge, right? Like. In either case, if you're prepping for an interview or even competitive, n squared is probably too slow for this one. So for these kind of problems, I actually don't. I mean, I know that I've said that is a well-known problem, but I don't remember or I don't memorize these things because it's useless to memorize, right? Like the idea is just try to think and maybe refigure out the invariant of this problem. And what is the invariant? Invariant is it's a property or something that doesn't change as other things are changing, right? So let's take a look at this problem and let's see if we can make any observation, right? So what does it mean by preorder? That means that for the first number that we see, that's going to be the root node. That's literally the order, because preorder goes, root, left, right, right? Recursively, obviously. But so that means that the 3 that we see is going to be at the root. So that means that we can literally construct from that. And then what does that do for the Inorder, right? Well, it means that everything to the left of the 3 is going to be everything to the left of the 3 is going to be on the left side of the tree, because in Inorder you do left and then the current node, which is the root or parent maybe, and then the right side, right? So what that means that here we know that the 3 is going to be the root. Here, just because that's how preorder always works, but then it gets ambiguous between like the 9 and the 20, because 20 could be the left of the 9 or to the right of the 9, of course, as well, as the parent or as the child node, the right child. But in this case, obviously, it's a sibling even, but that's where the Inorder will tell you. So now that we have that relationship where we have, okay, we know that 3 is the root, and that is the invariant here is that as you do a recursion, say, the preorder is always going to keep giving you the root, where the Inorder will give you, now that you can divide them in the left child, the root, and then the right child grouping. And then that's basically the idea, I think. And yeah, and that's And then it becomes just implementation detail. Is negative numbers okay, or is just -1 is a weird number? Okay, well, no, it just seems like, okay. I mean, shouldn't change anything. As long as they're unique, it doesn't matter what the whether the numbers are positive or negative, or even any number. Just 3,000 is just, I guess, some random number. So let's do that, right? So let's at least give it a try of what we just said, which is that, okay, for the pre-order, we know that the first node is going to be the root, and then in order, you try to find where that node is. And of course, if you do a naive scan, it is going to be n squared, right? Because it could be, for example, it could be a linked list, or like a reverse, or everything is it a linked list? No, I mean, yeah, it's essentially a linked list where everything's on the left or something like that. Then you loop through it, and it'll be all the way to the end and so forth, right? So the idea here is that, of course, anytime you do a loop multiple times to find an index of something, just hash it. That's basically the idea I'm gonna do. Yeah. So in order index, maybe. Naming is also hard, but so we enumerate in order. So we have index x is item in. So for this, is this the right notation? I don't even know anymore. I'm really bad at the fancy things. I think I should just stick to writing it slowly. Yeah, okay. Let's just write it in a silly way. So we set this, and then for index x in enumerated order, enumerate, we set the in order index of x is equal to index. And of course, one thing that I want to point out before I forget is that we can't do this because this is unique, right? They guarantee it to be unique. Otherwise, there's really no way of solving this, because if you just imagine pre-orders or ones or whatever, just one number, and in order is also one number, then it could be any of the Catalan combinations of possible trees, right? Catalan numbers. Maybe I'm saying that incorrectly, but yeah. Anyway, okay, a lot of trees is what I'm saying. So yeah, so based off the fact that it's in, so then now we move here, and okay, so then now we create the tree nodes one at a time. I'm just trying to think about implementation detail. We know the algorithm now, I believe. So yeah, so now we go. That's all. Yeah. I'm just trying to think about what's the best way to do this. I mean, it's going to be recursive, I believe, but yeah. Okay, let's just do root is equal to tree node of I'm just checking to see that there's at least one node. So yeah, pre-order of 0, and then root index of in order is just in order index of pre-order of 0, right? We want to return root at the very end, but not before we do a build, a recursive build, I guess, of the current node. And then the current node will have a left-right index, and this just describes the chunk of the in order that we use, because it's always going to be some contiguous part of it that we're going to do. So okay. So yeah, let's just build the root. We start with how do we want to write this? Maybe this? Yeah, okay. Maybe that's fine. Just trying to think where implementation's a little bit tricky in general, at least for me, because I'm really bad about I don't know, I've been on a bad streak lately, as you know, if you are a fan, you'll see, or just following, you could hate me and still follow, I suppose. But yeah, I've been kind of just terrible lately, so the haters are winning. Okay, so now let's, yeah, okay, maybe I don't need this here, but okay, for now, so we have the node, which gives us the value, and then the range left and right. So now we want to divide. Okay, we want to the syntax is a little bit awkward. So basically we want to put, I mean, might have to fix this up. So yeah, so what did I click on? Oh, that was the San Francisco weird link. Lucky I don't have anything dangerous on my passport. But in any case, yeah, root index is equal to in order index of node.route. Okay, so then the left side is going to be from the left. I'm trying to think whether it should be left or left plus 1. Let's just do something like this for now. There's a lot of work to be done, but yeah, but that's basically the idea. Oh wait, no, this should be left, not left plus 1. I'm confusing the preorder and inorder. Yeah. And this is way awkward. We do want to pre-process the preorder one at a time to keep on getting this root. So I'm messing up some. I'm just struggling a little bit on the silliness, but and of course we have to actually set a node thing. Man, there's definitely a cleaner solution, but I'm not finding it right now. So hopefully at home you're solving it in a quicker order. What am I doing again? Okay. Yeah, okay. So we want to yeah, preorder index, I suppose. I have to keep a global state, which is not great, to be honest. There are probably better ways about it, though. But okay, so now we built this. We looked at the current index. Okay, so now we built the left and then built the right. Okay, that sounds reasonable. So yeah, so let's actually set this up first. If root index -1 is greater than left, that means there's one element to the left at least. So then we do this. If right is greater than root index +1, then this happens. And of course, then now we do a left of node is equal to the new tree node of preorder index. Preorder index increment by 1, and of course we do the same for node that right on the right side. We have to do some funky stuff like non-local preorder index just so that we can manipulate it. But I think this is roughly it. I might miss something silly, but the idea conceptually should be roughly right. I got the wrong answer though, so maybe not. That's awkward. I hope that, okay, let's run it real quick, but that's kind of sad because I think on the other test thing they have a visualization, or maybe I'm thinking binary search. And in fact though, I'm missing some numbers, so that's just a lot of awkward. Oh, this is inclusive, so it could be one number, so okay, let's do that. Yeah, okay. So that was that. Whoops. Yeah, as I always say, and this comes up a lot in binary search, like when you do binary search, at least for me, but also in other stuff, is that be really clear when you represent a range. Be really clear to yourself. I mean, you don't have to like write down anything per se, but be really clear whether you're using exclusive bound, inclusive bound, and whether it's exclusive or like open or close on one side or the other or something like that. Because then now you would be able to tell that, if it's inclusive, that means that it's okay that they're equal, because that means that the range has at least one, right? So that's where I made that mistake and then found that out later. Did I submit? Like sometimes I forget to submit and people tell me in the video comments. Okay, cool. Yeah, so what is the complexity here? Well, for each node that we built, we only make, over one operations. So it's going to be O of n, where n is the number of nodes in terms of time. In terms of space, we Query does do some hashing here. Maybe you could be a little bit clever and not, but the way that we did it is recursive anyway. So it's going to be O of h at the very least, or O of h plus n, which is dominated by O of n in this case. So it's going to be linear time, linear space, including the stack space. That's all I have for this one. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Let me know if you did this one okay. Yeah, I mean, I know this is a well-known problem that may even appear in textbooks, and it's very tempting for that reason to kind of memorize the answer. But as you can see, I did everything from first principles, just trying to figure it out from scratch, and it should be doable, and you should be able to do it. And I mean, it's okay to remember stuff, but it's less okay, in my opinion. You do what you need to do to memorize, right? Because with practice, you're going to just have muscle memory, but that's not quite the same as deliberately just remembering and not understanding why or how these things come about, right? Like, like in future interviews, you may get the same problem except for this one twist, and if you just memorize a solution, you might not be able to figure it out because you don't have the you've been practicing or working on the wrong muscles. But anyway, all right, that's a little bit of a rant. It doesn't really matter. I'll see you later. Have a great rest of the week as usual. See you tomorrow. Stay good, stay healthy, help each other if you can, and I'll see you later. Have a good mental health. Bye bye.